All right, welcome. So I want to continue our series on proofs of correctness for greedy algorithms with another problem. This one I call museum guards, although it has a more common name, which would be interval cover, I believe, interval cover. And the reason why I wanted to bring up this problem is slightly different than the last couple problems we looked at. In the last couple of problems, the argument we needed to make in the proof of correctness was particularly mathematical, and that meant we needed to employ algebra, at least at some point in our argument, to prove that maybe one value was greater than another. And this is something that comes out a lot with optimization problems because we're often in an optimization problem trying to find the minimum or the maximum. And so it makes sense in our proof of correctness that we would have to argue that we've achieved that minimum or maximum. However, it is also often common that those arguments, the mathematical side of the argument, can be very simplistic, and there is still going to be some cleverness needed in other components of the argument, and those other components are usually logical in nature or part of the reasoning. And so I wanted to present another example. This museum guards problem is one where the math is going to be fairly simple, but we still need to reason about the choices we make to make sure that we're making the right ones. So let's take a look at the problem stated informally first. So here I've got an example about the city I live in. I live in Tacoma, Washington, and there's a famous museum here, the Museum of Glass. And the Museum of Glass, at least in this example, is hiring some guards for their next exhibit. And in the exhibit, there are going to be N pieces of art that are going to be displayed along a hallway. And each piece is placed at some point along that hallway. And for insurance purposes, the museum needs some guards, and the insurance companies tell them that they need to have a guard, a human guard, within 5 feet of every piece of art that is in the museum. The museum wishes to save money in hiring guards, so of course they could hire a guard for every piece or something like that. But the way they've set up the exhibit, some guards will be able to guard more than one piece of art, and they want to figure out the most cost-efficient way, and thus trying to hire as few guards as possible. And so our purpose is to take this sort of real-world-like problem, and our first goal here is to try and formalize it to isolate the information processing components of this real-world problem, abstract away all the details we don't need, and leave ourselves with just an information processing problem. So to do that, we want to focus in here and think, well, what is the input coming into this problem, and then what are they asking us to do? What is the expected output if we have that given input? So I think the one thing that I want to focus on here is looking at the pieces of art. There's a little n here that's already hinting to me here's some of the input maybe, because n is maybe the input size, how many pieces of art we've got. Now, what do we need to know about those pieces of art? The name of the piece of the art or who made it. These are probably details that we can abstract away. What's important to us is the placement of guards relative to these pieces of art, and we need to know where the pieces of art are so we can make that relative judgment. So we want to know of these n pieces, the locations, the points, if you will, along the hallway that they are going to be placed. And we can put this in some kind of measurement of distance, so let's say feet or meters. So let's presume our input is going to be n pieces with their locations, their points stated in meters or feet from the origin or the beginning of the hallway. And then we need to decide on the guards that we're going to hire. And again, our goal here is to have as few of them as possible. So that part there is sort of jumping out as being the expected output is the fewest number of guards. And remember, in an optimization problem, we usually have two different components. The goal is to know what the fewest number of guards are, but the museum is probably not going to be very satisfied if we come back to them and just say, yes, you only need 5 guards. They also want to know where we should place the guards so that they can, satisfy their insurance requirement. So we need to, in our output, have probably two components here. One, something expressing the minimum number of guards, and then two, something expressing where those guards are, and this extra criteria here, which is we want to make sure that the guards are guarding, well, all the pieces, every piece in the museum, meaning that we want to make sure that we can go, say, by every piece and make sure there's a human guard within 5 feet of it. So I formalized that idea that we just discussed there into two components here. The input, I've got those list of the pieces of art. I picked P for piece, and these are again going to be the locations of the end pieces of art, numerically stored here, again, maybe in feet or meters from the beginning of the hallway. And then the output here is going to be the guards. I call it G for guards. Now notice here N and K, these are different length lists. It's possible we have one guard for every piece. We don't need more than one guard for every piece, but we potentially could have fewer guards than we have pieces, and that's the goal, is to try and minimize K. So this is going to be the locations for our K guards, okay? And notice I'll skip to the end here where K is minimum, so that's where we're picking out that this is an optimal number of guards. K must be a minimum number. And then the rest of what I've got here is the conditions that's saying for each of the pieces, those are our PIs, for each of the pieces, there is at least one guard. There could be more, but we don't need to. There only needs to be one. There exists a guard, some GJ, such that, and now I've just tried to put this as formally as possible. This is just an expression of the within 5 feet requirement. Let's just see how I've done that. I've said take the location of the piece and then subtract off the location of this other guard, the guard that we say exists, and it should be less than or equal to 5. So we're just saying there should be some guard relative to each piece that we can find one that's within 5 feet. So the next question I have posed here are what are the conditions of validity and optimality for this problem? Now let's again revisit these ideas. A optimization problem usually is going to have two components for solutions to that problem. When you're looking for the maximum or the minimum thing, whatever it might be, whatever the solution might be to your problem, that usually presupposes that there are other solutions that are not the optimum, not the minimum or the maximum, that are acceptable in some way, and we call that way valid here, that are valid but are not maybe optimal. And the example I'd like to give is, say you were, getting change at a store and you need $1 worth of change. You usually expect to get, $1 change, and every once in a while, maybe the cash register has run out of $1 bills, and the attendant says something to the effect of, "Oh, I'm sorry, we're out of $1 bills. Will you accept 4 quarters?" 4 quarters is not the optimal way to give change, but it is a valid way to give change. And that's the idea here. We will accept it. We might not be happy with it. It's not the optimal version, but it is acceptable. And so that's what we're looking at here. For the solution to this problem, what are the conditions that would make it valid? And what are the conditions that make it optimal? And when we're looking for those conditions, they're usually both stored right in the output condition in here. We just need to go train ourselves a little bit with a little practice to find them, okay? And let's just look. There's really two conditions here. One is K is minimum, and the other is for every piece, there is a guard that is within 5 feet. And let's just think to ourselves, which of these is the validity condition and which of these is the optimality condition? So again, hopefully it sort of jumps out to you that having a guard that guards every piece, that's within 5 feet of every piece, that's the requirement from the insurance company. If we don't have that, the insurance company is going to cancel our insurance. So boom, that's not an acceptable solution. That's the condition of validity here. If we sort of fail the museum of guards and we're not able to come up with the minimum number of guards, but we are able to guard every piece, they will accept that solution because at least that preserves their insurance. But if if we are able to also achieve that minimum, then we have achieved the condition of optimality. So the minimum condition is usually, and this is another way that we can pick out the condition of optimality often, is usually in an optimization problem somewhere in there we're saying this should be minimum or this should be maximum. That's often the condition of optimality, which means whatever's left over once you distill that piece out is usually the condition of validity, and that's what we see here. That's what's left over. Okay, so hopefully we've hit those two pieces there. So let's go on and think about a strategy that we might use for these to solve this problem. Now you may have already at the top of your head a couple of ideas on how you might want to approach this, and that's good because in a lot of greedy algorithms there's going to be more than one solution. Sometimes those solutions are all correct, sometimes they're all incorrect if you've got a really hard problem, and sometimes, and more often, some of them are correct and some of them are not. And so we need to be able to tell the difference. And it's not going to be something that we can just look at them and say this one's correct and this one's not. It's a little bit of an intuition or art that we need to develop to build up our skills to be able to determine this. And then also when we do this, we usually, at least the way I approach a problem like this is, I don't know if the algorithm I've developed is correct or not. And until I do, I should be open-minded that it might be correct, but it also might not be. And so even though when I design an algorithm, of course, I hope it's correct, I want it to be correct, but I don't let that bias get in my way. I say, of course, I make mistakes, so it's possible that I've come up with an algorithm that's not correct. And so while I'm trying to prove it correct, I'm usually at the same time trying to pursue a counterexample. And that's because these two activities kind of serve to support one another, in the sense that if you're trying to find a counterexample and you're really failing at it, it's possible that that's because there is no counterexample. And whatever you're trying really hard to find a counterexample, whatever is getting in your way, that could be the secret to the proof of correctness that you want to write. And then vice versa. Maybe you're over there writing that proof of correctness and you're really struggling with it. There's one case that you can't get, and then you realize, oh, maybe I can take that case and build a counterexample. Maybe that case actually is wrong. And you can go back and forth. Often when I've got a hard problem, I'll go back and forth between these two until one of them becomes successful. Of course, only one of them can be successful, but you want to pursue both branches because you don't know ahead of time which one will be successful. And so to get a little bit of practice doing that, of course, we're still trying to build our intuition skills here. I want to start with an incorrect algorithm for this problem. And then try to come up with a counterexample for it. So the first idea I have here might not be the first idea that you came up with, or maybe it is. But again, just a pre-warning, this is an incorrect algorithm. So the idea here is to place a guard that covers the most pieces as possible for that guard. Okay, so the idea there maybe would be, since a guard can guard from 5 feet to the left, 5 feet to the right, we're effectively saying here a guard has like a 10-foot kind of range. So we're sort of saying here, find the 10-foot range that has the most pieces of art in it and put a guard there first. And the reason why we might think this is a good algorithm is often this is sort of the biting off the biggest bite you can in order to minimize the number of bites you need to make. That works in a lot of algorithms. It makes a lot of sense. In fact, the coin changing example I gave a little bit earlier is exactly that. Pick the bill or the coins that is the biggest, and that will minimize the number of bills or coins that you need to use to make change. So that's a good idea to have, and it's often one we want to try first. So we might have that same idea here. Pick a guard that guards the most pieces possible, and hopefully that will minimize the number of guards. And again, this is incorrect, so that means this can lead us astray. So let's think about that. So finding a counterexample means trying to come up with an input, an instance of the problem that if we ran our algorithm on it, our algorithm would give us the incorrect solution. Now, incorrect in an optimization problem means usually suboptimal. Okay, so we call this sort of suboptimal, meaning not optimal. Okay, but again, suboptimal implies in there valid. Suboptimal means we would accept this solution, but it is not the optimal, the best solution. Okay, now again, this coming up with a counterexample can be kind of easier than a proof of correctness, partly because we are dealing with just an existential quantifier here, meaning all we need to do is find one thing that shows that our algorithm is wrong. And if we find one instance where it is wrong, then that means it's wrong. Okay. On the other hand, if we're trying to prove it correct, it's the opposite condition. We need to show that there are no instances where it is wrong, meaning on every instance it is correct. And of course, there are infinite instances, so that makes it a more challenging thing to show. So counterexamples are often considered to be easier than proofs of correctness, but remember, you can only come up with them when your algorithm is false. So if you have a true algorithm, the proof of correctness is the only way to go. So one other little point that I like to make when coming up with counterexamples is the counterexamples are the easiest when the algorithm is the easiest. And this algorithm that we actually have here, covering the most pieces possible, technically is a little bit more complex, which means coming up with a counterexample isn't going to be super straightforward. And I'm going to show you my process of how I kind of go through to come up with counterexamples where you kind of build them. I might call it a process of construction. You start with something simple that maybe doesn't do what you want it to do, and you build it by adding more things onto it. That's what we're going to do here. So to get us warmed up here, we need to start thinking about the problem at hand and why our algorithm might lead us to error, might be wrong. Remember, in general, we might not know if we're right or wrong, but in this case, we do know we're wrong. So we know in this case that we're trying to minimize the number of guards. That's one of the important salient points we want to keep up. That's our goal. And then also the way we're trying to get there is by placing a guard that guards the most pieces possible. Okay, so I've got a kind of a question that I've posed here. This is a question that we could ask ourselves that will help us expose the error in this algorithm. So it says, when will placing a guard on the most pieces possible, as our algorithm is indicating, cause us to use more guards than we need? So what condition could possibly arise where placing one guard on all those pieces is bad? And the answer that, I know what the answer is, so I'm kind of trying to hint us towards the correct answer here. But another question or the answer that might help us is when those pieces that we're placing the one guard on, should actually be guarded by two guards instead. Now, why would that ever be the case? Now, we might, if we're really convinced our algorithm is correct, it's sometimes hard to come up with a counterexample because we might say, that will never happen. What do you mean? Of course, it will always be better to put one guard there instead of two. We're trying to minimize the number of guards. Well, let's see if we can wrap our mind around this, again, through a process of building up a counterexample. So starting from the idea that we want to put a bunch of pieces down that our algorithm will guard with one guard, but we hope the optimal solution will guard with two guards. Okay, now how we're going to get there is still a process maybe we don't know, so let's start. So again, counterexample is a bit of an art, a little bit of trial and error is used, and I usually just start by saying, okay, I know this might not work, but I want to just try by getting some kind of example down that I can work with. So I'm just going to start by placing some pieces that can all be guarded by one guard. So I've decided I'm going to place some pieces at position 10, 11, and 12. And let's just look at this instance for a second. All three of these pieces are within 5 feet. They're all within 2 feet. So if I place one guard, say at point 11, that will easily guard all three pieces of these. So these are easily guarded by a single guard. Now, this isn't the whole counterexample. That's clear to us as well because this can be guarded by one, but only one. If you put more than one, that would be wrong, but our algorithm says only to use one, too. So our algorithm is optimal for this particular input. And that's sort of what I've just said here. So we need to build a little bit more on that. So I'm going to add one more item. I've chosen to add this extra item. You see, I've added in an item at position 1 because this forces us so that we now need to use 2 guards to guard all the items. Let's just think about how we could guard them. First of all, I could put a guard at position 6. If I put it at 6, then 5 feet to the left is 1, and 5 feet to the right is 11, and that would guard the first 3 pieces, but not 12, so I would need another guard to guard 12. Or, what our algorithm would do, well, actually, we're not sure what our algorithm would do because that first group was of size 3 too. It could also grab these 3, right? And then we would need a second guard to guard 1. So again, we could guard all 3 of these, but say we put it as far to the left as possible. We put it at 0.7, so we got 12, and we're trying to get that 1. While it would only reach to 2, it wouldn't get 1. We would still need one more guard to guard position 1. So this needs 2 guards, but we're not even sure what our algorithm would do here because there's a tie. And when there's a tie, we didn't really say what our algorithm would do in a tie. But it would use 2 guards, and it would be, and that's the optimal solution. So that's still correct. So again, this is not a counterexample. This is not a counterexample because our algorithm, even though it's incorrect in general, would be correct on these ones. It would work on these ones. So we'll move to the next one, or we're going to try and build it a little bit more. Okay. So I mentioned here we could there's 2 ways to solve this. How can we build on this a little bit more? Well, one of the problems we were facing here was the tie. Our algorithm would pick this or this group of 3 because each are of size 3. We don't know which one it's going to pick. So what if we took that initial set we had there and made it a little bigger? Let's make it of size 4. So I'm going to add on one more. I'm going to add on the 13. Now the 13 onto that set means I can still place a guard at position 6. And that would guard 1, 10, and 11. And I would still need a second guard for 12 and 13. But notice that would be a set of size 3 and a set of size 2 when I could guard 10, 11, 12, and 13 all together with one guard, say placed at position 11, for instance, or as far to the left as possible at position 8, it would guard all 4. So we know that our algorithm will guard these 4, and then one more for the 1. But another algorithm, just some other random algorithm, might pick these 3 and these 2 and still get it with 2 guards. It still looks like it's optimal, okay? The idea here, and maybe some of you are seeing it, is if we really want the optimal solution to pick this group, the 1, 10, 11 group. So that means we want it to have a reason to pick this split instead of picking these 4. The way I'm going to do that, just like we have this 1 hanging off on the left here, I'm going to add one more element hanging off on the right here. So I commented that these are still optimal. I picked 22. Why 22? Because it's 12 plus 10. So that's far on the right hand side. I can place a guard at 17, which will hit 22 and 12, just like I can place a guard at 6, which will hit 1 and 11. And that way, those 2 guards will guard all 6 of these. But now let's think what our algorithm will do. It won't pick either of those because those only guard 3 pieces. Ours will guard 4 pieces, right? But then the 2 pieces that are left over, the 1 and the 22, they're so far apart, right? They're on the left-hand side and the right-hand side. We obviously need 2 guards to guard them. So completing this off. Now, this last one, this is our counterexample. Everything else up here, our algorithm works fine on. But when it gets to this one, our algorithm will end up having to use a 3rd guard when optimally, if we place it at 6 and 17, we get this one with just 2 guards. So this counts as a counterexample. Now, normally when you are trying to show a counterexample, it's not just the input, although the input is critical. It's usually these couple sentences around there as well, saying, hey, here's the input, here's what our algorithm would do. It would pick 3 guards, but notice you can do it with 2 guards, and 2 is better than 3. Okay, so this is one of those examples where the math involved, 2 is better than 3, is very, very simple. Everyone can see that. But the logical argument that's going to be involved might be still a little bit tricky and require a little bit of cleverness. All right, so we've dealt with this first idea. Maybe this was an idea that one of our friends or coworkers came up with, and we thought, hey, this could be correct, but it might be wrong. Let's try and figure it out. You were tasked with trying to find out a counterexample, and here you are, you found one. This is the point where you usually come back to the team and you say, hey, look, I found a counterexample. This algorithm's not going to work, so let's abandon this idea and let's go back to the drawing board and come up with some new ideas. So the idea that I want us to get started with, again, there's always a little nugget of cleverness that you need to come up with a good algorithm. But usually once you got that little nugget of cleverness, the rest you can do by just sort of following that path where it leads. So the little hint I want to give here is that you might be looking at whatever instance you have, and you realize no matter what, the leftmost piece of art, the first piece of art at the left side of the hallway, has to be guarded. So we need to put a guard on that. And once we start focusing on that, we can start saying, where is the best place for us to put a guard that guards that piece, the leftmost piece of art? And so I'm going to create here a fake instance. Okay, now this is a good way to explore a problem and try and understand how it works before tackling the proof of correctness or the trying to find a counterexample. But it's not a good way for conducting your proof of correctness, because this is one of the fallacies called proof by example. So just because our algorithm works on this example doesn't mean it's correct for all examples. We saw that just when we came up with our counterexample in the last slide. We saw 3 or 4 examples where our algorithm did work, but then we found one where it didn't. And so that's why this is not a good proof strategy, but it is a good way to explore your algorithm and try and figure out, this might inform you what a good strategy to take on your proof is. So in this case, we're going to try and use it to see if it can help us inform, maybe even coming up with just an algorithm. Where should we place the guard that guards that first piece? Now, you may already have an idea of it, but I'm going to start out with a very simple idea here, which says, well, maybe I start by placing it right at that piece. Okay, this is kind of naive, but maybe we say, okay, I'm going to place it here. Now I've also gone ahead and put a little range finder on there. That's sort of our insurance measurement tape or something. The insurance company says if there are pieces within that range, the guard is safely guarding them. Otherwise, that's outside the guard's range. And so we can probably see here that that's not the optimal way for us to, or place for us to put it. We could place the guard so that it is as far to the right as possible while still guarding that piece at position 1, which is where I've drawn it now. And you'll notice now it's able to guard this piece that it's also at position 11. Of course, I've strategically placed that piece there so that it was clear that this seems, or at least appears to be a better position for our guard than to place it only where we had it before. Now, I say appears because, again, this is not a proof of correctness. So just because this one case, it's obvious this one guards 2 instead of 1, that doesn't mean anything yet. That only means it's working here, not necessarily elsewhere. Now, we'll notice if we follow this idea, so now let's try and follow through. We don't know if it's correct or yet not, but can we turn this into an algorithm? Well, after placing this guard, we've got this piece guarded, we've got this piece guarded. Now this piece is unguarded, so we can repeat the same sort of idea. We could say, well, now we need to place a guard that guards this piece. Where should we place that guard? And again, we may place that one here. Okay, again, following our example out, we might place 2 more guards, and we can see that we can guard all of these pieces in my simple example here with 4 guards, which maybe is a little bit surprising since this is a 50-foot hallway. 5 guards we know would cover the whole thing, but we've been able to maybe save 1 guard. Okay, good. Now, the reason why I've also wanted to explore using this example, so maybe our algorithm is correct, but maybe it's not. We haven't proved it correct yet. But if it is correct, the thing I want to think here is, notice we did this by focusing on the leftmost piece of art. And there's nothing actually special about the leftmost piece of art other than, as English speakers, we usually read left to right. And so we privilege the left, but that's a matter of convention. Other languages and other speakers just start on the right. Why? Because it doesn't matter. When those languages developed, right seemed just as good as left, and they started on the right. And so we could imagine, what if we started on the rightmost piece of art? If we start on the rightmost piece of art, where would be the best place for us to place the guard? This guard, say, that's guarding the rightmost piece of art. This doesn't seem like the best place for it. So I've gone ahead and run that algorithm again, starting on the right-hand side. Now notice quickly, there are 4 guards again. That's good, 4 and 4. Okay, if the green ones are optimal, then the red ones are optimal, because the only measurement of optimality here is how many. So if 4 is the actual minimum, then both of these are optimal solutions, which means there is more than one optimal solution to this instance. And also, in general, for this problem, we should expect that there is going to be more than one potentially optimal solution. Okay, some instances you'll come up with there might be exactly and only one optimal solution, but those are going to be rare for instances of these problems. Most problems like this one I just made up. Okay, I put a little bit of effort into making the 10, the 1 and the 11 so that we could do that little explanation, but otherwise I just put some random dots on here. And what we see is that when I just put down these random dots, we ended up in a case where there was more than one optimal solution. And this is something we want to be sensitive to. In some optimization problems, we're going to have only one optimal solution all the time, and then others, there will be non-unique optimal solutions, and we should be sensitive to that. All right, so it turns out that algorithm is indeed correct. And in fact, both of those algorithms are indeed correct. And for a lot of greedy algorithms or problems that have greedy algorithms, there is usually more than one correct greedy algorithm. Some might be more efficient than others, but in this case, they're both equally as efficient as well. And so you can often come up with cases where there are lots of different correct, equally efficient algorithms for the same problem, in which case you just pick whichever one you like. And again, if you live in a left to right world like I do, then you pick the one that starts on the left and goes to the right. If you live in the right to left world, go ahead and pick the other one. It's equally correct and equally efficient. Now, the other cool benefit of that is if I prove mine correct, it also proves the other one correct, since we can do a very simple swap by just saying, well, turn all the items around, and now your algorithm is my algorithm. So that reverse the order, if you will. Start at the right-hand side, still to the left, and pretend the right is the left. However you want to set it up, both algorithms are technically the same. Okay, so that's what I'm going to do here. I'm going to set up a proof. And just like I've done in my last couple of videos, I'm going to prove this twice. I'm going to prove it once in a very elegant way, in the way you might see it written online. Those who have already completed their studies, writing for other people who have already completed their studies. And then I'm going to write one with a little bit more details filled in, so in case you're still completing your studies, you can see those details. Okay, so first of all, let's just look at the theorem. It says here, if we repeatedly place a guard 5 feet to the right of the leftmost unguarded piece of art, okay, there's a lot going on there, because what I've tried to do in that one clause is capture the whole algorithm that I've just described. Now remember, usually algorithms are complex, so we give a little bit of pseudocode for them. But greedy algorithms are often so simple, we can express them in one sentence or one clause, like I've done here. And if you can, go ahead and do it. If you can't, it's not a big problem. You can just write the algorithm above in a little bit of pseudocode, call it algorithm 1, and then you just say here algorithm 1. But I think in this algorithm was simple enough. So let's go through it again. Repeatedly placing a guard 5 feet to the right of the leftmost unguarded piece. So what are the key components there? Leftmost unguarded piece. That was important to our algorithm. So there's some hidden things there that's basically saying sort all of our pieces from left to right if they weren't already, and then start on the left. Okay, and then the only other piece we have there is that little advice. Okay, where do we place the guard? 5 feet to the right of that one. And repeat, and repeat. Okay, so again, we hope that if we pass this off to, a programming student, they'd be able to say, oh, I need a loop and I can write this, and they write it for us. We're going to prove it correct. So what are we trying to prove about this algorithm then? If we've now described the algorithm, what are we trying to prove? We want to say it's correct. Well, what are the conditions of correctness? Well, the museum guards problem that we came up with tell us the conditions of correctness here, minimizing the number of guards. Okay, now we also are going to have to come up with where they are placed, but the condition of optimality is just that they guard all the pieces of art. Remember, that's the condition of validity. That still needs to be in there. Every optimal solution is also assumed to be valid. So we need to prove that it's not only valid, but also minimizes the number of guards. So follow me with this more elegant proof for a second, and then we'll fill in some details. Now, in the previous couple videos, as I mentioned, our arguments tended to be a little bit more mathematical, and so we ended up needing some algebra. In these more logical arguments, I find pictures are more helpful. Now, the problem is I can't use the same picture I just used on the last slide, because remember, that's proof by example. That's just putting some examples down and saying, well, look, it works for this one, so it must work for everyone, and you shouldn't believe that. But so how can I draw pictures? Well, you can still draw what you might call general pictures. Okay, and those are pictures. You see I've got some ... dots in there. Those ... dots are saying, well, fill in the rest of this business however you like. Okay, because I'm trying to be arbitrary. And in some of those cases, that might mean fill it in with something, but also maybe fill it in with nothing. So for instance, over here, I've got a great deal of stuff going on here, and I've kind of tried to make it a little transparent, basically saying whatever happened until we got to this point in the algorithm, let's put it over there. But maybe this point in the algorithm is the beginning of the algorithm, so there's nothing over there. Or maybe this point in the algorithm is the end of the algorithm, so there's nothing over here. That's fine. I've just tried to set it up by saying, let's imagine we're running this on an arbitrary input and to get started. Okay, that way we maintain our generality. I'm not saying assume I've got pieces at position 10 and 12 and 15. I'm saying just imagine there's any old pieces. Okay, and I've tried to draw a picture to represent that, but let's again keep in mind we're trying to keep this general. So to get us started here, how do I start? I say consider the guard we will place, so that means our algorithm, to cover the leftmost unguarded piece of art. Okay, so here, I haven't technically labeled it here, but this circle here is the leftmost unguarded piece of art. I'm assuming everything up till this point has been guarded. Okay, so we've got this piece, and we've got this guard, so consider this guard, so that's what we're saying, and call this position G. So I'm just labeling this position G. Now, what I want us to imagine is placing this guard that we have here somewhere else at some other position other than G, and let's call that one G prime so we can talk about it. Now I've added to my picture here. The first statement I've got here is G prime cannot be further to the right than G because it would leave the leftmost piece unguarded. Okay, so for instance, this one with the big X in is saying we couldn't move it more to the right. And it should be obvious from our picture why this piece will become unguarded. And that would make our solution invalid. Remember, our solution must guard all the pieces. That's the condition of validity. So if we changed it in this way, it would no longer be valid. Okay. Now, that means this is an impossibility. We shouldn't consider that. So G prime must be to the left of the guard G that we were considering. Okay, so I've drawn another one over here. This one doesn't have an X through it because it's possible we could put our guard there. Remember on our last slide how there was 2 different ways to put the guards and it was okay? Maybe this is okay too, okay? The way I've drawn the picture, maybe there's a piece there, but ignore it now. Maybe that piece is not there, okay? Remember, this is just to help us out. Now, the part that I want us to focus on is this region here between the left-hand part of our guard and the left-hand part of where we've moved it. There's an objection we might raise that says maybe there are pieces here that the green guard is guarding that the red guard is missing out on, and that's why the red guard is wrong. Now we're trying to argue that no, that's not right. The red guard is correct, and this green guard, while it may be correct, it doesn't invalidate the correctness of ours. And that's what we're trying to argue. So how can we argue that? Well, again, by looking in this region between where our guard can't guard and over here, there might be pieces. The way I've drawn it, this piece might be there. But the way I've drawn it, because we assume that this was the leftmost unguarded piece, because this one's the leftmost unguarded piece, this one must already be guarded. So if our green guard also guards this piece, we now have doubled up on the guards. It's great that the green guard's guarding it, but we didn't need the green guard to guard it because there was already a guard over there guarding it. So that's the last bit. There are no unguarded pieces to the left of the leftmost unguarded piece. That's by the definition of what a leftmost unguarded piece is. So there are no previously unguarded pieces that are guarded by our new guard, the green guard, that are not also guarded by G. Okay, so G guards the same number of new pieces as G prime. Even though G prime might guard more, it's doubling up on those other pieces. Okay, now it's possible, the other thing that we haven't actually said here, and this is the conclusion that I'm about to get here, it's possible there's this piece here, in which case our red piece is indeed guarding more pieces. Now remember, thanks to the counterexample we just gave, guarding more pieces isn't always, the best, but what we're saying here is the red piece here, or the red guard, guards at least as many pieces as the green one. So it's definitely not worse than the green one, and that's all we need to say that ours is the best. It's not worse than the other ones. And that's our last conclusion. So a guard placed at position G will guard an equal number or more pieces than any guard also placed to guard this leftmost unguarded item. So how does this help us with our proof of correctness? Now, the reason why I call these ones sort of a little bit more elegant, but they're also a little bit harder to digest, is because it seems like we didn't do the whole proof of correctness here. I focused in on only one guard, and I said, look, this guard is just as good as any other guard. And so there's a lot of machinery wrapped around this that says, well, what about the next guard? How do we know the next guard is correct? Well, we might say, well, let's go look at the next guard. The next guard will be in this exact same situation as this one. And even if you placed all your green guards the way you placed them, that doesn't mean placing the red guards the way I've placed them is incorrect. So now let's go and try and add more machinery to this, because if this is feeling sort of incomplete to you, it's because there might be missing out some of those pieces around, filling in the gaps. Let's fill in those gaps. Okay, so the theorem's going to be the same here, but we're just going to try and prove it with a little bit more details so we can fill in those gaps. So the first thing I'm going to do is I'm going to put the setup and make it more explicit. This is a setup that other proofs are just going to assume you can do on your own, or assume you already know is necessary. And that's really assuming a lot of our reader. And so I'm going to go ahead and state it to my reader. Even if you knew this already, now you know that I know it as well, explicitly. So the first bit is trying to make sure you know that even though I've drawn this picture down here, that this picture is intended to be a general picture. So I'm going to start out by saying, assume we have an arbitrary set of pieces of art. And then I'm also going to assume, prior to the proof at least, maybe not prior to the algorithm, but prior to the proof, that they're already in order from left to right. Why? Because that's the order that we're going to consider them. That's the order we want to consider them in our proof. So let's keep them in that order. All right, next, I want to be explicit about what I'm talking about here. So I've got the reds and the greens down here. I'm going to give them names. I'm going to say S are the positions our algorithm will place the guards from left to right. So I've got some red ones over here. And then O are going to be the positions of a collection of optimally placed guards from left to right. Okay, here I'm saying optimally placed, meaning I'm not making any other assumptions about how they were placed other than they're optimal. Okay, meaning they have the minimum number of guards. All right, so I've got them. Why am I doing this? So I can compare them to each other. I want to compare the reds to the greens. Why do I want to compare S to O and the reds to the greens? Well, if they're the same, then I know, since I know that O is optimal, if they're the same, I will then know that S is optimal as well. All right, I'm going to, often at this point we will say, well, if they are equal, then we're done. So I'm going to skip that line just to save myself some space on this slide. But instead I'm going to say, let's go to the first point where they disagree. Notice this has an implicit assumption that they must disagree somewhere. If they don't disagree anywhere, we don't even have to go down this branch. Okay, so we're going to assume that they disagree somewhere. I'm saying let I be the leftmost guard, that's going to be this guard here, such that SI is not equal to OI, meaning the position that we put guard, the ith guard for S is at a different position than where we put the ith guard for O. Okay, at this point there is a leftmost piece of art that is not guarded by the first I-1 guard. So these are the first I-1 guards. Notice I've drawn the green ones and the red ones to be the same. Because, how do we know they're the same? Well, we said let I be the leftmost guard such that they're different. So that means all the ones before had to be the same. This is the first one where they're going to be picking different guard locations. Okay. Now at this point, all the pieces that were guarded by S were also guarded by O, so we can pretty much pretend like they're not there. We're just gonna, ignore them because they're all the same over there. Okay, so instead we're gonna focus in on this one. This is the leftmost unguarded piece. So that's what it's saying here. At this point, there is a leftmost piece of art that is not guarded by the first I-1 guards. Okay, sure. Focus in on it. Call it AI. Okay, this one will be called AI. All right, now we need to, okay, so now we're actually going to that last proof. That last proof has the important components in it that we want, but remember it left some of the pieces out. These are some of the pieces it left out, but now we're getting to the part of the proof where we can borrow from what we just saw, okay? So we had different names over there. We had G and G prime. Over here we have different names. We're calling them SI and OI, but we can still talk about them in the same way we did over there. Okay, so first of all, we're going to say if OI is to the right of SI, that's what we have here. Okay, it leaves AI unguarded, and thus it is invalid. That means it's impossible. We assumed up here that O is optimal, and implicit in optimality is validity. So since we have assumed O is optimal, we know this case can occur. So again, on my picture, I just drew an X through it. No, you can't put your guard over there. So what did this mean in the last proof? It meant we had to put our guard to the left, right? We needed to put our guard to the left if we're going to put it in a different location. So OI is to the left of SI. So that's what we know now here, all right? Now, I'm going to do something here that I sometimes call a swap argument, or I sometimes call doing surgery to my solution here. I'm going to take O, which is my optimal solution, my green solution, and I'm going to change it. I'm going to say, what happens if we take out this OI and we replace it with SI? Or another way of saying that is just moving it over here, saying, what happens if we move that guard from where it was before to where our solution puts it? Okay, so let's look through the verbal version. Now imagine replacing OI and O with SI to get O prime. So after this change, we don't have O anymore. We now have a new solution. And for the moment, because I want to talk about it, I'm going to call it O prime. Okay, so after the swap, we have O prime. Now, since all the pieces to the left of AI are already guarded, remember, all these ones are already guarded by the red guards, but also the green ones, because the green ones were in the same positions as the red ones. Okay, moving this guard now does not leave any pieces unguarded. So even though this green guard might have used to be guarding this piece, it was already guarded. So moving the green guard over here does not leave any pieces unguarded. So we're arguing this because it means if we haven't left any pieces unguarded, we're still a valid solution. Remember up here, it became invalid. That was wrong, right? So we want to make sure we're still valid. We are, okay. In addition, what did we do? We took one guard away and put one guard in, or the way we drew it here, maybe we just moved one guard. So the number of guards we have is still the same. So we're still optimal. We haven't added more guards to get to this state. So O prime is still optimal. And the important thing is it's now in agreement with S. Remember how this argument started? We said, let's imagine there's an S, let's imagine there's an O, and let's find this first place where they disagree. Well, now let's go back to the beginning. And let's assume there's an S, but let's say the O that we picked out is O prime now, not O. Since O prime agrees with us on this point, we can get past this point. Now when we say let I be the leftmost unguarded, that might be a different one, or none at all. If it's none at all, we're done. We've now shown that S is optimal. If there's another unguarded piece to the left, now that we try and repeat this argument, so the next part is we can continue this proof with O prime in place of O. And we can repeat this argument for all their disagreements. Let's say there's another disagreement. Okay, we'll do another swap then. In that case, we might get to O prime prime or O double prime, and then O triple prime and O quadruple prime, and we might have to do n changes. But at the end, we will again have shown that ours is optimal. So this is the reason why this is true, or the reason we need to deal with this kind of argument where we're making the swap, is because there's more than one optimal solution to this problem. So imagine now that we were trying to run our proof on this set of instances, on this instance, and we've got our solution. Our solution are the red ones, right? But let's say the optimal solution we're trying to compare it to, the O we're trying to compare it to, are the green ones. Well, we will start and we'll notice they already disagree on the very first element. And when they do, we could move that first guard to be in the same position as the red's first guard, and we will see that the new one, which will be O prime if we've moved that one guard to the right, will still be valid, still be optimal, and now agrees with S. And we can do it to the next one. The next one will move over now. Once we move this one over to agree with this one, we can move this one over to agree with this one, and then we can move this one over to agree with this one, and move this one over to agree with this one. After 4 changes to the green solution, each change we make, it will still be valid and optimal. After 4 changes, we've changed it into our solution. And since after each change, we've changed it from one that was valid and optimal to another that's valid and optimal, we know when we get to the end and the solution we have is our solution, that it must also be valid and optimal. And that's the essence of this proof and how it works. You'll notice we didn't use any algebra in this proof, just some logic. I really find the pictures help. The picture is not necessary for the proof. So the verbal version of this alone is all you need to actually demonstrate this. But I find the picture really helps both your reader try and follow along, and also helps you think about the proof when you're trying to write it. So if you're trying to tackle some proofs of your own, feel free to go out there and start drawing some diagrams and pictures to help you wrap your mind around it. All right. Thanks a lot for watching. We'll see you in that next video.